Okay, so this set of questions relates to magnetic fields and induction. And this one here is a similar setup to the required practical, I believe it's number 9, where it's finding the force on a wire. So we've got the experimental setup here. Okay. And the magnets produce a uniform horizontal magnetic field. We have a copper wire DE. It's connected to the circuit as shown. Okay, so what we need to look for here is what direction is the current going to be going. Current flows from positive to negative. We are dealing with conventional flow. So current is flowing this way, and therefore it's flowing from E to D. So that's our current. Okay, here we go. We say that the apparatus is assembled so that when the switch is open, we're reading 0, so it's been zeroed, and the reading changes to a positive value when the switch is closed. So that means that something is pressing down on the scale, okay, or on the top pen balance, if we want to be precise about what we're saying. Which of the following correctly describes the direction of the force acting on the wire, okay, due to the magnetic field when the switch is closed? So, if we look at our yoke, okay, we look at our scale, the wire is not what's pushing down on the scale, okay? What's pushing down on the scale is the yoke, which is being pushed down because of the force on the magnetic field. Okay, so the force on the magnetic field is down, which means the force on the wire must be going up. Okay, equal and opposite reactions. So it is going vertically up. Label the poles of the magnetic or of the magnets by putting N or S on each of the 2 dashed lines. So for this here, okay, we know that our current, which will be our second finger, is going from D to E. Okay. The force is going up on the wire. That will be your thumb. So that means that the magnetic field will be going in this direction. So that means that, remember, the magnetic field lines always go from north to south. So we've got south and north. All right, defining a Tesla. So a Tesla is defined as the unit of magnetic field strength unit of magnetic field strength where you have 1 Newton of force for every 1 amp flowing through 1 meter of wire. Okay, so you really need to have all of that information there, that it's 1 Newton that you are getting 1 Newton of force for every 1 amp per meter. Okay, that's really the only way to define what the Tesla is, because that's what it is. Okay, so here we go. Our magnets are 5 centimeters long, when the current in the wire is 3.43 amps. The reading on the electronic balance is 0.62 grams. 0.620 grams. Okay, assume that the field is uniform and is 0 beyond the length of the magnets. Calculate the magnetic flux density between the magnets. Okay, so formula we need F equals B I L. Actually, I should do a lowercase l just to be consistent. So BIL. Now a couple of traps in this here. So the traps that I can see are we've got 5 centimeters, okay, and 0.620 grams. Okay. So for this here, we need it in meters. This we need in kilograms, so that we can convert it to newtons. Okay, so the actual so F is also equal to M times G in this case. So what we have is then M times G equals BIL. I want to solve for B, so B is equal to M times G divided by I times L. So 0.620 times 10 to the minus 3, or 10 to the 3, not minus 3. Oh, not a highlighter. To the 3 times 9.81 times, it's going to write over there, it's not going to write over there. Alright, let's erase all that and write it out smaller and neater. Okay, so 0.620. Oh no, it is 10 to the minus 3. Times 9.81 for G. Oh, I need to have more. Alright, and all that is divided by our I, 3.43 times 5.00 times 10 to the minus 2. And if we math all that out, 0.620 minus 3 times 9.81. Three. And I get 0.035 Tesla. Okay, if you got an answer like 35, you probably forgot a power of 10. 35 Tesla is like more than an MRI machine. So 0.035 Tesla. All right, that's question 1.